Hi students, welcome to your sketch notes on standard deviation, standard error of the mean, and error bars. You will want to make sure that you have these sketch notes in front of you so you can add the notes that I add and highlight anything that you want to make note of. So we will not actually be calculating standard deviation or standard error of the mean on any of our assessments. I'll show you how to calculate them, but these values will be calculated for you already, and then you will use the value standard error of the mean to help you to draw error bars. They look like this on bar graphs if you're given a set of data. When we see this abbreviation SD, that stands for standard deviation, and then standard SEM stands for standard error of the mean. So when we look at standard deviation, essentially what this is doing is telling us how clustered our data is to the mean or how spread apart our data is from the mean. So if we have a very small standard deviation, that means that there's not a whole lot of variation away from that mean in our data. If we have a larger standard deviation, that means that the data is spread farther away. So for example, let's say that you had some values of 10, 20, and 30. You add these up, divide by 3, your average is 20, but there's 10 units in between each one. Now if you compare 18, 20, and 22, you actually still have the same average of 20, but the data is closer together. So you would have a larger standard deviation with this data, and you would have a smaller standard deviation with this data, even though the average is actually the same. So again, our standard deviation is going to measure variation in our data values. The formula for calculating standard deviation is here. So this is not something that you actually have to calculate. We will use Google Sheets and Microsoft Excel to calculate for us, so you do not have to calculate this. And then standard error of the mean is going to measure the accuracy of the mean. It's going to tell us whether the mean is really precise or less precise. The bigger the standard error of the mean, that means the more spread we have in the data. You can think of it like the bigger our standard deviation would be. And then a small standard error of the mean means the data is more precise, meaning the data is more clustered together. So when we look at standard error of the mean, if we're using plus or minus 1 standard error of the mean, that will put us at 64% confidence. So that will tell us that our data lies in this average or in this range 64% of the time. But if we do plus or minus 2 standard errors of the mean, that will put us at 95% confidence. So we are actually going to use that plus or minus 2 standard errors of the mean so that we can work at a 95% confidence value, which basically means that our true average lies in this range. So it might be this range, it might be this range, 95% of the time. So we might say, oh, this is the average, but the true average lies between here and here 95% of the time. Obviously, that's a really big range. Or we might say, oh, the true average is this, or the average is this, and the true average lies between here and here 95% of the time. Again, this is much more precise. It has a smaller standard error of the mean. So when we graph standard error of the mean, we're going to graph plus or minus 2 standard errors of the mean. So this little dot here would be what your actual average is, or your mean. And then going up or down would be plus or minus 2 standard errors of the mean. So you will go up 2 standard errors of the mean and down 2 standard errors of the mean. So if you're only calculating SEM, you would have to multiply that times 2. So SEM times 2, you go up that much and down that much from your average to make your error bars, because we always use plus or minus 2 standard errors of the mean. So plus 2 and minus 2. We'll do lots of examples in class. When we're calculating standard error of the mean, we'll use this formula. S would be the standard deviation, and N would be the number of samples, so sample size. So you can see that you can have the same standard deviation for 2 data sets and actually have a different standard error of the mean. The more samples you have, the greater your N is. So if you have like 1,000,000 samples, a standard deviation divided by 1,000,000, it's going to give you a small number. If you have that same standard deviation, but you only have 10 samples, then you're going to end up with a larger standard error of the mean. So one way to get smaller standard errors of the mean is to have more samples. Our standard error of the mean allows us to infer how much that sample mean matches the true mean. So basically our confidence in our data. And again, we're going to work at this plus or minus 2 standard errors of the mean confidence level, or 95% confidence. So we're going to use set SEM times 2. So if you are given SEM, again, you have to multiply that times 2 to get SEM times 2. And that'll give us our 95% confidence interval. So let's say that we have 3 samples, 1, 2, and 3, and we have our average, our standard deviation, our standard error of the mean, and 2 standard errors of the mean. Now you might say, well, how did I get this average? What are the different trials? I didn't include the separate trials. So there might be 10 trials here, 2 trials here, and 20 trials here. I didn't actually give you all that background information. And by the way, it's kind of hard to see the decimals here, so you can add those in. So what you would do if you're graphing this, you graph the averages. So you can see that for sample 1, the average is 0.220. So we're going to put our data point here and draw our bar graph. And just kind of a heads up, if you're like, how did you know to do a bar graph and not a line graph? Well, these are just called samples 1, 2, and 3. It's not like a numerical value. And you might say, well, 1, 2, and 3 is numerical. Well, I just called this sample 1. I could have called it sample A, sample B, and sample C. So there's no numerical value units associated with our x-axis. So anytime it's categorical, then you're going to use a bar graph. So I graphed my mean here. And then our first sample 2, my mean is 0.215. So I'm going to put my little dot here and draw my bar graph. And then for sample 3, our average was 0.208. So I'm going to plot that and then draw my bar graph. And then we need to add in our error bars. So for our error bars, we want to do plus or minus 2 standard errors of the mean. So we can calculate standard deviation using the formula up here. We can calculate standard error of the mean from our standard deviation. So we have SEM. Then we have to multiply that times 2 to get plus or minus 2 standard errors of the mean. And this is already calculated for you. I will be giving you a spreadsheet that will calculate these values for you for your Oreo lab or anything that you need to calculate these for in our class. So this value is already calculated for us. We're going to use this to make our error bars. So when we have the average of 0.220, we need to go up and down 0.0078. So we're going to go up 0.0078. So basically 0.220 plus 0.0078. So if you add that on your phone or your calculator, so we're going to go 0.220 plus 0.0078. That means the top of this error bar needs to go up to 0.2278. And then we need to do our average minus 0.0078. So that would be 0.220 minus 0.0078. And that tells us how low we need to go for our error bars. And then we will do that for each of our data sets. So again, our average for sample 2 was 0.215, so we need to add 0.0086 to that, so we know how high and how low to go for our error bars. And we'll do the same thing for sample 3. So we'll go up 0.0084 and down 0.0084 from the mean. Now you'll notice, since we're going up and down the same amount, the error bars should be equally tall as they are short. Well, I guess that's not really, they should be symmetrical across this. That's what I mean. So this should be the same length as this. And this should be the same length as this. That does not mean that this needs to be the same length as this, because look, those numbers are different. But above and below this little average should be the same length. So what this average, or what these error bars mean, is that even though I'm saying the average is 0.220, the true average actually lies between this and this number. We're 95% confident it lies between those numbers. And we're 95% confident that the true average for sample 2 lies between this number and this number. So even though we calculated the average, the actual average doesn't mean that much. It's the average plus or minus the 2 SEM that means more. So we have a 95% chance that the true mean lies within this range here. And now we can compare these. So before the error bars, you might say, oh, sample 1 has a higher mass than sample 3 because this average is higher than this. But look, the error bars overlap. And let's talk about what this means. When error bars overlap, that means there is a chance that all 3 samples have the same mean because they all overlap. Or that the mean of sample 1 could actually be lower than sample 3. So the true mean of sample 3 might be up here and the true mean of sample 1 might be down here. So we have to say there's no significant difference in the sample means anytime the error bars overlap. Now let's pretend, and this is not something that you need to write down, let's pretend like the error bars for sample 1 looked more like this. Okay, so if the error bars for sample 1 look like this, they overlap sample 2, but didn't overlap sample 3. So we would say there is no significant difference between sample 1 and 2, but there is a significant difference between samples 1 and 3, and 1 has a higher mass than 3. So just keep that in mind. Again, you don't have to draw that on there. So if there's no overlap, then that means there is a significant difference in the means. And then you can actually say, oh, this one is higher than this one. So I hope that's helpful. If you need more time, just rewind.